Section 3.1 Complex Numbers. Expressing square roots of negative numbers as multiples of I. If a value in the radicand, so that's a number inside the radical, is negative, the root is said to be an imaginary number. The imaginary number I is defined as the square root of negative 1, meaning the square root of negative 1 is equal to I. Definition of a complex number. A complex number is a sum of real number and an imaginary number. The complex number is standard form when written as a plus bi, where a is the real part and bi is the imaginary part. Every number can be written in standard form. If there is a lack of an imaginary number, we can think of it as 0 plus your imaginary number and an I. Let's take a look at this example. Express the square root of negative 9 in standard form. Well, I can work with that negative and write an I. So if I just deal with that, I have I square root of 9. If I take the square root of 9, we're left with 3. But just like variables, we like to write the number first. So we have 3i. Notice there's an absence of a real number. So to write it in standard form, our answer would be 0 plus 3i. Plotting a complex number on the complex plane. In the complex plane, the horizontal axis is your real axis, and the vertical axis is the imaginary axis, as we see here. So instead of x, we have the real and the imaginary. So let's go ahead and plot the complex number 3, negative 4i on the complex plane. So I didn't provide a grid. Let's go ahead and draw a Cartesian plane or an imaginary plane. Let's draw 5 tick marks on each side. All right, instead of labeling it as the x-axis, we label it as the real axis. And instead of labeling it as the y-axis, we write an I or write imaginary. Okay, so just as before, think of this as a coordinate point. So we have 3 and negative 4i. So if in relation to the past, this would have been like a 3 comma negative 4. So let's plot that. So we have 3 along the real axis and a negative 4 along our imaginary. We want to see where they meet, so our answer would be this point right here. Just like when you're graphing in a regular, real Cartesian plane. Adding and subtracting complex numbers. Just as with real numbers, we can perform arithmetic operations on complex numbers. To add or subtract complex numbers, we combine the real parts and combine the imaginary parts. Think of this as combining like terms, where you add your x's and your numbers without an x. So a quick example, what if you had 2 plus 3x plus 1 plus 4x? Wouldn't you add your x's and add your numbers without an x to have 3 plus 7x? Well, that would be the same practice we apply to adding and subtracting imaginary numbers. So let's go ahead and do this first example. Let's add 3 minus 4i and 2 plus 5i. So we go ahead and we add our real numbers. 3 plus 2, that gives us 5. And work with our complex. Negative 4 plus 5, that gives us 1. So plus 1i, or just I. So the answer is 5 plus I. Let's do the next example. Subtract 2 plus 5i from 3 minus 4i. So we're going to subtract 2 plus 5i from 3 minus 4i. Okay, so let's go ahead and work this out. So let's start off by, you can distribute in your negative. So that you have 3 minus 4i minus 2 minus 5i. And we can go ahead and combine like terms. So let's add our reals. 3 minus 2, that gives us 1. And our complex, negative 4 minus 5, we get negative 9. Negative 9i. And this would be our answer. Let's continue with multiplying imaginary numbers. So when multiplying, we follow the same rules and applications that we learned with real numbers, such as distribution and the FOILing method. Just keep in mind that when we have an I squared, it's the same as negative 1, which we have here. Okay, so let's take a look at this first example. We want to find the product of 4 times 2 plus 6i. Let's begin by distributing this 4 into our parentheses so that we have 4 times 2, that's 8, plus 4 times 6, 24. So we have 8 plus 24i as our answer. Take a look at the next problem. We're asked to multiply these two sets of binomials. So we have to FOIL so that we have 4 times 2, that gives us 8. 4 times negative 5i, negative 20i. Negative 3, not negative 3, 3 plus 2, 3i times 2, plus 6i. And lastly, 3i times negative 5i. So we have negative 15i squared. So let's go ahead and combine like terms. We have those i's we can combine. So I have 8 minus 14i minus 15i squared. Now don't forget that I squared is the same as negative 1. So let's multiply in that negative 1. So that we have 8 minus 14i plus 15. 8 plus 15, that gives us 23. So our final answer is 23 minus 14i. Dividing complex numbers. We need to find a new term by which we can multiply the numerator and the denominator. That will eliminate the imaginary portion of the denominator so we can end up with a real number, a denominator. The term is called the complex conjugate of the denominator, which is found by changing the sign of the imaginary part of the complex number. Or, as I like to think of it, just changing that middle sign. Okay, so this first example is just helping us establish what a conjugate is. So example, find the complex conjugate of each number. So for A, I have 2 plus 5i. I change that plus to a minus. So our conjugate would be 2 minus I squared root of 5. Next problem, we have minus 1/2 I. Now, it's easier or it's helpful if you write it in standard form. So I have 0 minus 1/2 I. Therefore, its conjugate would be 0 plus 1/2 I, or just positive 1/2 I. Okay, let's do an example. Divide 2 plus 5i by 4 minus I. So let's write it 2 plus 5i divided by 4 minus I. So our goal is to get the I not in the denominator's place. To do that, we must multiply by the conjugate. So we're going to multiply by the conjugate of the denominator, which would be 4 plus I, 4 plus I, and we multiply. Okay, we're left to FOIL, so that we have 2 times 4, that gives us 8. 2 times I plus 2i, 5i times 4 plus 20i, and 5i times I plus 5i squared. In our denominator, notice it's a difference of squares. So yes, you can FOIL, or you can remember that it's your first term squared minus your second term squared. So let me write that hint above. A squared minus b squared is equal to a plus b, a minus b. So this is what we have, and if we multiply it, we get what's on the left. So that we have 4 squared minus our second term, I squared. If this is tricky, you can always FOIL. Alright, so we are left with 8. 2 plus 20, 22i. And then we have the I squared, which you know it's a negative 1. So this gives us a minus 5 divided by 16 minus I squared is negative 1. So that we have 8 minus 5, which is 3 minus 22i. And then 16 minus negative 1, we get 17. And that is how you divide with complex numbers. Next example, just like with a function, we can also evaluate. We can go ahead and plug in a value into x. So this example reads, let f of x equal x squared minus 5x plus 2. Evaluate f of 3 plus I. So this is saying for every x in our function, we're going to substitute in 3 plus I. So that we get x squared, 3 plus I squared, minus 5 times x, which is 3 plus I plus 2. All right, let's begin by FOILing, multiplying this out. So this is 3 plus I times 3 plus I. And if we multiply this out, we'll get 9 plus 6I plus I squared. Let's multiply in that negative 5. And that gives us negative 15 minus 5I. And then we have a plus 2. Remember, I squared is negative 1. Okay, let's combine like terms. I have 9 minus 1 is 8, plus 2, we have 10, minus 15, we have negative 5. And then 6i minus 5i plus 1i. And that is our answer. So we can say f of 3 plus I is equal to negative 5 plus 1i, or just I. All right, next example. Let's evaluate when f of x is equal to 2 plus x over x plus 3. Evaluate for f of 10i. So we're going to replace each x with 10i. so that we have f of 10I is equal to 2 plus 10I divided by 10I plus 3. All right, that is our answer, and we could box it, but then when you go check into the back of the problem, you would see it doesn't match what we have. The reason for this is because, just like before, when you had to rationalize the denominator, you always want to make sure you do not have any i's in your denominator. So let's go ahead and proceed by multiplying by the conjugate. So next we multiply that 2 plus 10I divided by 10I plus 3. We're going to multiply by the conjugate. So I have 10I minus 3, 10I plus 3. And this is the conjugate of your denominator. So that we need to multiply 2 times 10I, we get 20I. 2 times negative 3, negative 6. 10I times 10I, 100I squared. And 10I times negative 3, negative 30I. All right, in the denominator, we know that should have been a minus, not a plus. In the denominator, we know it's going to be the first term squared minus the second term squared. So I have 10I squared minus 3 squared. Okay, let's clean this up. So in my denominator, I have 10 squared is 100, and I squared is I squared, minus 3 squared, that gives us 9. In my numerator, I can combine those i's, 30 and 20. So 20I minus 30I, negative 10I, minus 6, plus 100, and I squared is negative 1. Okay, let's clean up our numerator. So we have negative 10I minus 6 minus 100. In our denominator, same thing. We have 100 times I squared, which is a negative. We have negative 100 minus 9. Okay, let's clean this up. So we have negative 6 minus 100, which gives us negative 106 minus 10I, divided by 100, negative 100 minus 9, negative 109. And there we have it. Now, if we like to, we can go ahead and write it in standard form. Also, notice you can divide out a negative 1 from all of this. So this 109 is dividing both of the numerators, so that we have 106 divided by 109 plus 10 over 109i. All right, last bit, simplifying powers of I. The power of I are cyclic, meaning they go in a cycle. One that's missing is I to the 0 power. What's anything or any real number to the 0 power? With the exception of 0, we have 1. Okay, we see that there's a pattern going on with our answers. We have 1i, 1i, 1i. And notice that there's negatives combined with these. So I have positive, positive, negative, negative, positive, positive. And if we continue, we get a negative 1 and a negative I. So I to the 6th power we know would be a negative 1, and I to the 7th power would be negative I. And it would continue that cycle. So if we wish to evaluate a value that is over our list, to do so, we want to try to think of that exponent as a factor of 4 because that will help us work with our I to the 4th power, which is 1. Okay, so we have a 35. So 4 times what is the closest number to 35? Well, we know 4 times 4 times 9 is 36. That goes over. So one less, we would have 4 times 8 is 32. So 4 times 8 is 32. You would have to add 3 more to get to that 35. Okay, let's do that with our exponents. So we have I, and we have I raised to the 4 times 8 plus 3. And I'm replacing that with 35. So we can write this to be I raised to the 4 times 8 times I to the 3rd power. Okay, so we know that I to the 4th power is just 1. So we're left with 1 to the 8th power, which again also gives us 1. But what is I cubed? I cubed is negative I. So we're left with negative I. So we're left with 1 times negative I. So our answer is just negative I. Okay, for the section, your homework is 5 through 43, every other odd. All right, so this was section 3.1, complex numbers.